everyone. Welcome. How's minibar going for you? Yeah, thank you. Yeah. This is one of the best things about the Twin Cities. No exaggeration. I love minibar wildly and without reservation. Hi, my name is Paul Cantrell. I teach at Macalester College. I do freelance software stuff around town sometimes, often with Bust Out, great people. And I'm here to do something that I rarely actually do in my teaching life, which is give a talk. Most of my teaching is spent hands-on. We do a lot of getting your hands dirty activities, and today instead I'm just gonna point at a bunch of stuff on the projector that I think is cool, and mostly my talk is, that's cool. Isn't that cool? I hope you think so too. I decided to go for high content, so I'm going to speed run it a bit, but I'd love to field questions if there's any time at the end, and I'd love to talk to you after. Please find me, and you can find me on Mastodon, which is, unlike Twitter, not a hellhole right now, and it's actually shockingly good. Find me there, ping me, try it out. All right, I've got a little puzzler for you. Anybody want to guess what this is? That's a very good guess, and no, the box in the upper left is the ENIAC initiating unit. But there's a clue. You found it right away. This is related to the ENIAC, which, depending on who you talk to, is maybe the first general-purpose electronic computer. This is ENIAC related. What is it? It's code. That is code. That's a very good guess. That's a program. What I'm talking about right now is early programming languages. The thing you're looking at right there is a piece of an algorithm. Now, if you guessed wires, you're right. This is a computer that you programmed by plugging wires into jacks, patch cables. The way this computer worked is it had a bunch of logic units that were already just sort of pre-made and fixed, and you created an algorithm by plugging them into each other in different ways. Obviously, we don't write code like that anymore, right? We replace patch cables with something much nicer and much higher tech, which is this. Anybody recognize that? That's a punch card, yeah. What you're looking at, I won't parse it all right now, but basically each column is like a character or a byte of data. And yes, it is full of holes, and yes, you have to punch them by hand. There's a machine that helps you punch them. And in later years, there were machines that would even like hook a keyboard up to a punch card. But you entered code by punching these damn cards and running them through a computer, which was, I mean, it was hideous. Mercifully, I missed that by just a few years. But surely, this punch card represents text, right? So if we take the text that's on the punch cards and put that on the projector, then we should see, finally, something familiar. Shortcode in the upper left was arguably the first high-level programming language. By the way, that's not like hexadecimal or something. That's actual code. I won't decode it all now, but for example, x3 is a variable name. Yeah, this looks wacky, right? Our languages just don't look like this. This talk is about change. I'm here to talk about how change happens in programming languages. And I'm here to talk about a specific kind of change. This stuff doesn't look just weird. There's stuff in these languages that we don't have anymore. Like, for example, right down here, APL is famous for using all these weird characters. Like, what the hell is that? I don't know, actually. We don't use that anymore. That character exists in Unicode because some nerd thought it was good to be able to represent this obscure language from the 60s. Actually, APL still has a huge fan following. But like autocode in the middle, line 3 there, that arrow T means something different than the plus T in the next line because it's in a different column. That is a language where you're not looking at indentation. Different columns mean different things. So the horizontal position of something changes its meaning. We don't do that anymore. This talk specifically is about things disappearing, which is interesting, right? We have this idea sometimes we fall into this trap where we think that progress is the accumulation of better and better things. We add features. And why not just add features, right? Like, if I have a programming language that does some stuff and I have a better idea, I add that, and now it does more. The best thing is to always add, right? Right? I think anybody who's written code for any length of time knows that actually deleting code is the best part of programming, and this is true of programming languages too. Deleting features is what language designers love. And I love looking at things disappearing because it's a great lens to use to ask questions about what programming languages actually are. If you take anything from this talk, I hope it's a newfound curiosity, a newfound perspective, maybe a new way of seeing the languages that are in front of you and thinking about what they really mean, what they are, what to be paying attention to, a perspective that's not just the daily headache of, oh my God, this code doesn't run, and how do I do this? And I'm searching Stack Overflow, and will ChatGPT help me? No, nothing helps me, it doesn't work, right? Let's get some perspective. I'm gonna talk a little bit about the past. We got a taste of that, and we'll have another taste of the past. I'm gonna make some predictions about what might disappear in the future. I'm just gonna speed run a few arguments for why I think some very common language features might go away. And I'm going to provide some timeless lessons about programming languages for you to take home and treasure close to your heart. So the title of this talk is, what's the next GOTO? GOTO is a thing that disappeared. To answer that question, I just want to look first at what's GOTO. Has anybody actually written code with GOTO in this room? Yeah, nice. All right. Hey, some old timers. Yes. Yeah. Here's an example of GOTO. This is my first programming language, AppleSoft Basic on the Apple II Plus. Can you make a reasonable guess about what this code does? Yeah, sometimes, but it only goes to line 40 if x is less than or equal to max. The thing to note here is that the lines are numbered, and the reason they're numbered is so that we can go to them. Also, that's how text editing worked on the Apple II Plus. It didn't actually have a proper editor. You had to type in a line number and retype it to replace it, or add a line number in between to insert text. It was terrible. Don't miss it. People complain about text editors now. Yeah, in a modern programming language, this is just a multi-line if statement. And I would venture, actually, that the version on the left is maybe a little easier to understand. If you've never seen code before, this indentation business is weird. Maybe there's curly braces. What the hell are they? The thing on the left, that's kind of how people write recipes. They write instructions for things. You go to WikiHow, it looks like that, right? GOTO has a kind of nice, intuitive beauty to it. Here's a puzzler for you. What would this be in a modern programming language? Take a minute with it. Yeah, does anyone? It's totally an if-else statement, right? So here's what's awesome about AppleSoft. It doesn't have else. It doesn't need else. GOTO does it. You can build multi-line if statements and if-else out of nothing but single-line if plus GOTO. That's awesome, right? I think it's awesome. Isn't that awesome? Yeah, check this one out. Now we have a GOTO that goes backwards. What's going on here? That is totally a loop. Could write it as a for loop, while loop, whatever. AppleSoft doesn't care. You don't need loops in this language. You can build them out of GOTO. GOTO is awesome, right? We stuff all these complex language features into modern language, and all you need is GOTO. It's so simple. Like this. Check this out. What do you think that is? I'll draw in the arrows to help you out. You got it? Do you see the pattern? Here's the pattern. Yeah, that on the left, that is a hot mess. That's the technical term. Yeah. So what's wrong with that? Does the computer have any trouble executing the code on the left? No, it's fine. The computer doesn't care. The thing on the left is a problem because we have to read it. I don't know if whoever wrote that code knows what they were doing. It was me. I was just trying to make it complicated. It doesn't mean anything. what I definitely know is that a person reading that code in the future is going to be lost, right? So here's the first one of my timeless lessons about programming languages, is that these languages are for humans. We forget that really easily. Programming languages are for humans. They're also for machines, right? That's sort of the defining characteristic of a programming language. But really, the thing that makes programming languages what they are is that they have to be machine readable and human readable at the same time. That's what makes them complicated. If we only made programming languages for machines, we would just write a bunch of binary machine code, who knows, right? Programming languages and their many features and their many structures, they're there for us, which is a really easy thing to forget sometimes. It feels like programming languages are magic technology that was handed to us from aliens and stone tablets from outer space. And no, actually they were like, this is all of these features that we write code with are people trying to help you write code, trying to help make it possible for you to write code. Programming languages are for people. It is actually possible to express the thing on the left in modern structured programming. You might be able to simplify that, not much. It really is a hot mess. But honestly, if I'm maintaining this code, I think I'd rather work with the one on the right. I feel like I have a better hope of actually untangling what's going on with the one on the right. I personally, I'm not going to lay that down hard. At least I can follow through it. At least I can see where it goes forward, where it goes back, what might happen. Here's the thing though. People at the time did not feel that way. And by at the time, I mean like in the 1960s, conditionals, if statements, and loops started entering programming languages. And they were controversial. They're unnecessary features. They make it too hard. You just need GOTO. People in the 60s love that shit on the left. They loved it because it's simple and it's elegant, and there's some things that you can do with GOTO that are really hard without GOTO, and a fight broke out. People loved GOTO because they were used to it and they knew what to do with it. So 2 timeless lessons. The first is, it's all trade-offs. That thing on the left was simpler. The thing on the right maybe is more comprehensible, but it also requires more language features. It's all trade-offs. So this is a really important insight. What's a trade-off? A trade-off is when you gain something and you lose something. What does that mean? If it's all trade-offs, that means that making progress requires losing things. Programming languages are all trade-offs. And remember, people loving that GOTO on the left, Paul loving the one on the right, maybe you too. Actually, I don't love it, but if I have to choose, here's the other timeless lesson we can get from that fight. We're very bad at judging things. When things are familiar, we misjudge them. When things are unfamiliar, we misjudge them. The unfamiliar is either scary or magical. It's either unthinkable or it will solve all of our problems. The familiar, we love it, we hate it, but our reactions to things are mostly about how familiar we are with them. We're much better as humans. We're much better at reacting than we are at imagining. And that really colors how we see programming languages. Here's the thing. This fight went on, and it got really hot when somebody went and proved mathematically that there's nothing you can do with GOTO that you can't do with if and loop. Everything that's possible with GOTO is possible with conditionals and loops. This led to a movement called structured programming. And structured programming, Algol was the language that it was its standard bearer. It's also, by the way, the first programming language that you would recognize as seeming somewhat familiar. Structured programming said, just stop using GOTO. It's bad. Just always use loops and conditionals. A huge fight broke out. The fight famously culminated in this, it wasn't even an article. It was more like a letter to the editor that Edsger Dijkstra wrote. Dykstra is this very famous, very brilliant, very cranky and opinionated computer scientist. He was often right. He was sometimes quite wrong about things. He gave a talk about software engineering and how much he hated the term in the 80s that I think is really wrong in fascinating ways. But in this case, his argument was, look, GOTO is terrible, and here's why. I'm going to give you this quote, and then I'll summarize it. Dijkstra's argument was, our brains are pretty bad at imagining things happening over time, and they're pretty good at imagining things in space. And the job of a programming language is to make the layout of the code in space explain how it's going to unfold in time. And he asks a very specific question that helps us see the problem with GOTO. Here's some imaginary code, bunch of GOTOs, some of those might be conditionals, right? And we ask the question, okay, suppose we're at that line of code right now. We just stop the program. Suppose we want to erase everything and restart the program right here. How much information do we need? And if you ask that question, it leads to the question, how did we get here? So how could we have gotten to that line of code? How many different possible paths through the code are there to get us to that point? It's hard. It's hard to figure out what has happened already if we know where we are in the code. Whereas in structured programming, here's imaginary modern language with lots of indentation. In structured programming, if we ask the same question, we don't know. There's multiple possibilities. Maybe there's a conditional that happened before and we did or didn't take it. Maybe we've been a certain number of times through a loop. We can't know everything about what happened, but it's a pretty easy question to frame, right? The program goes from top to bottom. We either took each conditional or we didn't. The loop repeated or it didn't. If there were function calls, we can look at the call stack. The structure of structured programming gives us a way to break down the question, how might we have got to this point? What can have already happened if we're at this point in the code? And being able to answer that question lets us refactor code, extract code, delete code, figure out what depends on what. If you try to extract something from a program that's full of GOTOs, it's really hard. Does anything GOTO here? Whereas the code on the right breaks down into subunits within subunits. It has this nice tree structure that makes it comprehensible and rearrangeable. So Dijkstra's argument is it's not enough to just use structured programming. Get rid of GOTO. It makes things worse. Removing things can actually make a language more usable and it can make it more powerful. And there was this huge decades-long fight, but basically Dijkstra won. GOTO is rare. Almost no new languages include it. In languages that do include it, people mostly pretend it doesn't exist. We use it very carefully in controlled environments with great caution. The next timeless lesson here is that removing features can actually improve languages, and we have removed GOTO. It is dead. GOTO is done. Except this is the result of a disassembler running on some machine code, Apple Silicon machine code. This is modern. Those arrows, what are those arrows on the left? Oh no, oh no. Oh, that's GOTO in disguise. Here's the thing, GOTO is still with us. Assembly language is 100% GOTO. We didn't actually get rid of it at all. We just let compilers turn structured programming into GOTO so that we don't have to think about it, and thank goodness. My fifth timeless lesson here is that actually removing things sometimes just means abstracting them away. Sometimes we don't delete this thing from reality. We give ourselves a simpler way of thinking about the same problem that hides the complexity behind. That's really the heart of software in so many ways, I think. All right, so how y'all doing? With me so far? Are you ready to hear some prognostications, some bold predictions? I'm going to speed run 4 things that Paul thinks probably are going to disappear from programming languages. Every one of these I'd love to talk for like an hour and a half about, and I'm going to try to be quick. But I'm sorry if it goes fast. Send me questions after. What is the next go-to? I have 4 candidates. I think raw memory access might actually just disappear altogether from most programming languages in the near future. Already mostly has. That one's kind of low-hanging fruit, actually. I think inheritance might disappear from object-oriented languages. Is that provocative? Have I surprised anyone? All right, yeah, thanks. I think reference types might disappear. Reference types means like I pass you some data and now we're sharing it. And the last one, just in case nobody's shocked yet, I think null is on the way out. Yeah, all right, well, nice, all right. If a fight breaks out in the audience, like the premiere of The Rite of Spring, I'll feel like my mission is achieved. All right, raw memory access. What is it? Probably some of you have never worked with it. Congratulations. Raw memory access at this point, by the way, it mostly means C and C++. If you look at the list of like, yeah, C was one of my early languages. Right after Pascal. I love C. It has a special place in my heart. If you look at the list of like the 20, 30 most popular programming languages, most widely used programming languages, C and C++ and Objective-C are pretty much the only ones that actually have full-on raw memory access. So what I'm talking about here is something that is right now isolated to a few languages which are kind of feeling a little defensive about it. The best way I can explain, if you're not familiar with this, the best way I can explain what it is to lean on XKCD, Randall Munroe, the great mind of our time. Here's a person asking a server, I sent you the string bird, and please reply back with my string. Give me 4 characters back. So here over on the right, see, here's all this stuff that's in memory. And in the computer's memory, there's stuff everywhere. One piece of code owns one bit of it. Another piece of code owns another bit, but it's all just in memory. And the server dutifully finds those 4 characters, BIRD, and sends them back. And then our friendly attacker says, send back hat, which is 500 letters long. And the server dutifully sends back whatever 500 bytes of memory there are, starting with HAT, and it includes somebody's password and somebody's... Okay, this is not hypothetical. This is the Heartbleed bug. This actually happened. This happens a lot. What's the problem with raw memory access? It is a security flaw factory. It is a fire hose of critical vulnerabilities, and also it's a fire hose of bugs. It's really, really, really hard to manage memory yourself, to work with arrays that don't check their bounds, to work with raw pointer arithmetic. The bread and butter of C programming causes problems at a very, very, very high rate. So what's the solution? Well, the solution has kind of come in 2 phases. And the first phase, the reason that most programming languages now are memory safe is that they're very abstract, and they apply a whole lot of runtime safety checks. So for example, if you write Java or Python or Ruby or JavaScript, and you try to ask an array of 4 characters for its 100th element, the programming language says no. When your program is running, it checks that you're not going beyond the end of the array. That's a runtime safety check. Automated memory management, garbage collection, and reference counting are also examples of runtime safety guarantees. People love to hate on Java, but I've got to say we owe a debt of gratitude to Java, which in the 90s sort of proved that somewhat performance-sensitive code can tolerate the expense of all these runtime safety checks. Before that, memory-safe languages had mostly been sort of like, oh, they're like script languages, and they're for beginners, and they're for little kids, and real programmers work with raw memory. And Java came in and said, you know what? Raw memory access totally prohibited, and look, you can write awesome software with it, just as long as you don't mind the 3,000 year startup time and using all of the memory that your money can buy. Java's great. I don't know why Google chose Java for Android. It doesn't make any sense. It's so memory hungry and power inefficient. It's weird. They made it work, but like, what? Different talk. The second phase of getting raw memory access out of the picture, however, is, I would say Rust is by far the best example of this. There's been a bunch of really interesting research in static safety around memory access. Static means analyzing the code before it runs. And if you use the language Rust, there are actually pointers to raw memory running around, but there's also a bunch of really strict rules about how you're allowed to share them. And it turns out that the kind of static analysis that Rust does produces code that's very, 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 very close to as fast as C. And it lets you do basically all of the same kind of bit twiddling low-level stuff that you need to do with C, but it's memory safe. You can't do stuff like that XKCD cartoon in Rust. Remember, one of our timeless truths here is that it's all trade-offs, right? So what are the trade-offs? I just made it sound so much better. The big trade-off is performance. Raw memory access lets you write the fastest code possible. And the other trade-off, surprisingly, is convenience. There's just a bunch of programming idioms that are a lot easier if you can take the address of a variable and pass that address around. You can do some pretty cool stuff that way. Right now, the performance benefit is shrinking to almost nothing. It costs very little to have memory safety in a language like Rust, and the cost was already pretty low in even more abstract languages. And the convenience benefit is something of a mirage. The clever things that you can do with pointers are more convenient when you're writing the code than when you're debugging the code. I'll just leave it right there. Raw memory access, I think it's on, but okay, so wait, is it really that much of a problem though? Like if you need the fastest code possible, shouldn't you just use C still? It's been around forever and it works, right? Microsoft did a systematic study of where their critical security problems were coming from. They found that 70% of their critical security flaws were caused by memory errors, meaning these are flaws that simply could not exist in a memory-safe language. Google did a similar study and found a similar result. I also came up with around 70% of critical security flaws. The NSA just last year freaked a whole bunch of people out. It's the NSA, right? They're like, what do they ever say in public? And what they said in public was, stop using C and C++. They're like the cigarettes of software. This is like toxic waste, right? Don't. This ruffled a lot of feathers. But the gauntlet is down at this point. And personally, I think this cake is baked. Like, this is already on the way out. C and C++ are going the way of Cobalt. Anybody know what Cobalt is? Cobalt is the first programming language that was really popular in businesses. It's from the 50s. It's ancient. People were making fun of Cobalt and saying how it was already dead when I started programming in the early 1980s. Cobalt is dead. Okay, so when we talk about things disappearing and languages disappearing, what we really mean is for new projects, when we have the choice. Actually, Cobalt is alive and well. Did you know that Cobalt became object-oriented in the late 80s and early 90s? You can do structured programming in Cobalt and just avoid GOTO altogether if you want to. A lot of the time, the lessons of newer languages help us write better code in older languages, but we don't get to get rid of older languages entirely. That's not actually a thing. My last timeless lesson here is the past is never dead. It isn't even past. Anybody know the quote? It's William Faulkner. Nobody remembers the play that it's from. They remember the play for that quote. I don't remember the play. I don't know. It's called Requiem for a Nun. But yeah, the past isn't gone. We have trilobites, we have Cobalt, and we're going to have raw memory access forever. But we're going to choose not to use raw memory access in the future. You ready for another one? I'm going to have a go at inheritance now. Inheritance. What is inheritance? Inheritance is when we combine is-of relationships with code reuse, right? I'm saying, like, this thing is a screwdriver, and so it inherits all of the code that makes things a screwdriver. And I want to use it as a doorstop, screwdriver doorstop. So I just copy all the code from screwdriver and then say it's also a doorstop. Something like that's the basic mechanism of inheritance. So, like, what, inheritance? Really? It's already on its way out. Some of the inventors of C try to make a newer, better programming language, and they choose not to include inheritance, even though it's kind of object-oriented. 2015, making the new, better systems language, which totally has subtyping and objects and method dispatch. No inheritance. They left it out. You cannot do it. Apple, replacing their flagship language, they didn't quite get rid of inheritance, but it is greatly de-emphasized in Swift. Swift developers mostly stay away from it for greenfield modeling. It's there mostly because of interop with older APIs. And even Java, Josh Block, swell person who wrote like array list and hash map, no big deal. Josh Block in mid-2000s in effective Java says, favor composition over inheritance. Composition means has-a relationships. Okay. So why? What's the problem? I'll just zip through. This is a lecture I love to take 45 minutes to do, and we're going to do it in 3 minutes. Sorry. Here's a bookshelf that has an add method, right? I want to make a subclass of bookshelf that counts how many books have been added to the shelf. No problem. I add an instance variable called count. And now I just need to override that add method to make it do whatever it does and also count the book being added. There it is. With me so far? No problem. Here's the problem. Bookshelf has a second add method that lets me pick which shelf I want instead of just choosing the next available one. So to make it work over on the right, I've also got to override that method. Otherwise, books added to a specific shelf might not get counted, right? Here's the problem. On the left, that add method that adds it to a specific shelf, it's implemented by calling the top method and then setting the shelf. So what happens if I call counting bookshelves second add method? I add book to shelf 3. Okay, first I add the book. That calls counting bookshelves add method, and count is incremented. Then I set shelf, and then I increment count again. Actually, the bottom method increments the count twice. But that's okay, right? I don't add it. No, but there's a huge red flag here. Here's the huge red flag. That was supposed to be secret. The whole point of object-oriented programming is that objects encapsulate some things. They make some things secret. That was supposed to be hidden. And I have accidentally revealed the contents of this method somehow through inheritance. The way that method is implemented is not secret anymore. Inheritance breaks encapsulation. That's only one of inheritance's problems. Inheritance only supports a single axis of specialization. What do I mean by that? Really quickly, I'm just going to do a hand wave example here, okay? I'm making a game character object for my RPG, and I want sword-carrying game characters and fireball-shooting game characters. So I make fireball game character and sword game character. Cool, and they both extend the parent class, right? So I have an abstract method, attack, and the subclass says how attack works. No problem. Now I also want some characters to be able to fly and some characters to be able to walk. That means that I need to override the move method. Now I have 4 subclasses: sword, fireball, walking, and flying. But the walking and flying ones don't say how to attack. The fireball and sword ones don't say how to move. So now what do if I want like a flying sword game character, and who doesn't, right? Then I have to somehow like combine those two. So one of two terrible things happens. Either you have a language like Java that says you can't extend multiple classes, or you have a language that lets you do that. And it turns out the second choice is even worse than the first. It creates this thing called the diamond problem, which is just a rabbit hole of things that you have to tiptoe around. It gets very messy very fast. This is one of those programming language things that looks like a wormhole and is actually a black hole. You think you're going to make it through, and it just goes down. And you can work with it. You can make code work. People write code with multiple inheritance that's just fine, but it's a minefield. The third problem with inheritance, yes, there's more. It's really, really hard to honor the Liskov substitution principle. I'm paraphrasing it here. Right. If I say Paul is a person, then everything that's true about people should also be true about Paul. Inheritance is a relationship. So if we extend something, then everything that's important about the superclass needs to stay true about the subclass, right? So that we can substitute a value of that subtype in a place that expects the supertype. Cool. So here's a brain teaser for you. If I'm making classes called square and rectangle, should square extend rectangle or should rectangle extend square? Which is it? Where's the is-a relationship? A square is a rectangle, contrary to many elementary school teachers. Cool. So square extends rectangle. Okay, what properties does a rectangle have? It has a width and a height, and you can get and set each of them. It has 4 right angles, but we're already screwed. If I can change the width and I can change the height, then that has to be true of a square too. So my square subclass has to do something to make it so that even if I change the width and the height are still equal. Well, I can make it so that if you change one, you change the other. That leads to wild and fascinating bugs very, very quickly. I'd love to run through this. It's delightful to watch how every attempt to make this relationship work in object-oriented programming just completely fails. If you try to do rectangle extending square, because look, rectangle could add a width or add a height maybe to something that already has a width, right? Wouldn't that make sense? It also goes haywire. There is no actual way to make this relationship honor the Liskov substitution principle in OO, which is hilarious because a lot of textbooks use this as their introductory example of inheritance. Oops. What is the problem with inheritance? It does all this. I'm just going to summarize that as to say it makes big code tangles. It's very hard to model stuff with inheritance in a way that actually makes the logic of your type relationships work out. What is the solution? It's 2-part. The first has been around for a long time. Use what Java calls interfaces, or what Python and Ruby and JavaScript don't give a name because it's implicitly how everything works. What you do is you have a point of polymorphic abstraction and you put it behind a has a relationship. That's very technical, so I'll just give an example and let it sit there. In the game character, we say a game character has a attack. There's an interface that's like, what does an attack need? And then there's several implementations of attack. And then game character also has a movement method. And there's several types that implement movement method. And game character delegates any work related to motion to that one has a relationship. It delegates any work related to attack to that other relationship. You can have arbitrary combinations of those things. They don't interact with each other. This pattern right here, interfaces plus delegation, that's what Josh Block is talking about when he says, avoid inheritance. And then if you're really adventurous, the second half of where inheritance goes is type classes, which are an idea that come from ML family languages, particularly Haskell. But the thing to look at if you want to understand them is protocol extensions in Swift. I never really understood type classes until I saw protocol extensions. I'm just going to wave my hands at this one again. Give me a nod if I'm making sense. Subclassing says, I want to use a screwdriver as a doorstop. Therefore, I need to make screwdriver extend doorstop. And the screwdriver has to know that it is a doorstop. Type classes say, no, 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 no. The screwdriver doesn't have to know anything. Here's a screwdriver plus, separately, instructions for how to use it as a doorstop. The screwdriver does not know that it is a doorstop. The person using it doesn't know that it's a screwdriver. They just have instructions for using it as a doorstop. Problem solved. This sounds like a very hand-wavy thing. It's actually a shift in how virtual method dispatch works. You use witness tables instead of itables. But the philosophical shift of, no, 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 no. It's the person providing it as if it is a doorstop who explains how it's a doorstop rather than the object itself. That turns out to solve a huge number of problems. What's the trade-off? Always the question to ask. The trade-off is this takes a lot more upfront work to think about. And also, people are still figuring out how to do this well, particularly the type classes. There's not a lot of good models in non-esoteric research code of how to make this work well. Google Swift protocol extensions, if you want to learn more about this. It's fascinating. Can I give you a quick taste of why reference types can go away? So what are we talking about? Real quick, here's some JavaScript. What's this code going to print? I've got an array of two things. I log it pre-schnitzel, and I print all the things. Then I add schnitzel with noodles to the list. Push means append in JavaScript, because JavaScript is catterwampus. And then I print all the things again. And here's what it prints. Why? Because this crappy print each method deletes things as it goes. It works by deleting each item. Shift means remove it from the front. It works by deleting each item and then printing it. So when I call it the first time, it totally empties the array. What's the problem here? The problem is that the code on the left passed its array to the print each function. It shared it. It passed a reference to it. Then print each unexpectedly changed it. And when we continue, the array that we shared with this other code has been modified, and we didn't expect that. This unexpected mutation of shared code is a major source of bugs and confusion in programming, and it's a problem in basically every modern programming language. Not just John picking on JavaScript, because that's always fun, but Python, Ruby, Java, C, C#, the whole lot of them. What's the solution to this? The solution is just make everything immutable. Don't let anybody modify anything. If you want to have any kind of new data, you have to make a whole new value, whole new object, whole new something. Everything immutable. Is that really practical? Well, there is a language that does this called Elm, which I highly recommend doing a little research. This has been a thing in research for years. Elm is a lovely, approachable language with great documentation that actually makes it possible to understand this. And to convince you it's possible, here's the game of asteroids implemented in Elm. This is, again, a language where everything is immutable. And every frame of animation is just making all new everything. And it totally runs smoothly, in a web browser, no less. All right, so how is this possible? Well, here's the secret. Remember I said sometimes removing actually means abstracting away. Elm secretly is full of mutable data. But just like GOTO, we don't see it. We pretend that everything is immutable. And the compiler turns it into mutable stuff when it can. We don't have to think about GOTO, and with Elm, we don't have to think about mutation either. Okay, so how do you actually write an application this way? Here's the way an Elm app works. There's a function that gives you the initial state of the app. There's a function that, given the state of the app, says, here's what should be on the screen. I've got this data, cool, here's your UI elements. And I've got a function that anytime something happens, an event could be like key pressed or time passed. Every time something happens, we produce a whole new state of the entire application. Those three functions are an Elm application. Here's the beautiful thing. If everything is immutable, then the result of calling a function can only depend on the inputs to the function. If I call the same function with the same inputs, I get the same result every time. You know what that means? You can record all the inputs to the app. A fun exercise that I have my students do is write a time machine. You can feed any app into the time machine, and the time machine starts recording all the past states, and then you can pause it and just rewind time and recover any past state of the application. That's something that we can do not just because there is immutability, but because there is only immutability. This does not work if we have shared mutable state in the language. There's a variation on this called everything copied. It turns out that this is equivalent to everything immutable. In C, if you just like always use structs and no pointers, you basically get the same effect. And this actually is where the action is. We're almost out of time now, so I'm gonna finish on this one. The trade-offs of this is that it's really young and it requires deep re-architecting of the code, and you can't shoehorn it in. That's one that I missed here. What I just described is actually what React is trying and failing to be. The problem with React is that it takes an everything is immutable attitude and shoehorns it into a language where everything is mutable, and it doesn't end happily. And we didn't even get to null. I'm so sorry, but the clock is against me here. Thank you all so much for coming. If you want to hear about null, come find me out in the hallway. And I think we're at time now, right? Yeah, we are. Thanks, everyone.